Today we're going to start doing hypothesis testing, and this is by far the most important subject of the class. We're going to be looking at three different types of hypothesis testing, and the first one is what this video is about. We're going to be testing for the mean, and we're going to be using a test where sigma, the population standard deviation, is known. So what we're going to do then is let me go and get all of the information that I want to use in the problem and then show you how the structure of these things works. So what we have is this. Here's a claim being made. Is it true that these cans are producing or these cans are holding less than 16 ounces in any significant way? Is that true? So a natural thing to do would be to grab some cans of pop and see what the volume is on them. And if they appear low, then we might have a serious problem. So the point of this is to test whether they whether we have a significant problem or not, and it's going to be based on the sample that we take. So what we have here, a soda pop manufacturer, he wants to know if his cans are being underfilled. To test this claim, he's picking out 100 cans, and he does find they're low, 15.8 ounces. Now he's going to use a statistical test to determine if that's enough evidence to suggest there's a problem, or if this was just a sample that by sheer probability happened to have an average that was low. So what I'm going to do is I'm going to write up a few things here while I look at the problem. For one thing, look at this. We know the 100 equals n. The average volume here was 15.8 ounces. So let me put that as what we call X bar. In particular, we're going to be using the distribution of the mean. The population standard deviation is 1.2, so that's what we call sigma. So that's given to us. And then when we talk about the mean being less than 16 ounces, we'll say that mu equals 16 for the purposes of this problem. Now here's how you set up a statement here. What we have here is I write two things down, H sub 0 and then H sub A. These are referred to as the null and alternative hypotheses. So the first one is called the null hypothesis, and the second one is the alternative. I'll just say alternate. Now, the alternate hypothesis is always a problem that involves an inequality symbol. And in fact, here, if we look, we're testing to see if our mean is actually less than 16 ounces. Remember, mu is the population mean, and we're really testing to see if mu is less than 16. We're hoping it's 16 because that's the stuff we're selling, but let's check and see what the stats tell us. So what I put here in the second line is I put mu is less than 16, and that's called the claim. The opposite is true for H naught. So whatever you put in H sub A, you need to put the opposite in H sub 0. It needs to be a contrary statement. So the opposite of a less than symbol is a greater than or equal to symbol. Then what we do is we draw a picture. Here I'm going to put the proposed mean in the center. Now this arrow is pointing to the left, indicating less than. And notice our sample, in fact, is over here somewhere, 15.8. And what we're going to do is look at the area of the region to the left of 15.8. And we're going to compare that with this thing here, the 0.05, which I haven't mentioned yet, but this level of significance always goes by the name alpha. What we're going to do is compare this region with alpha. And so we can't do anything with this region until we get a z-score. So let's do that. Now remember, we're talking about testings for the means. So we have to remember the symbols that we're using here. So there's the two symbols. Now, mu x equals mu, that's no big deal. That's going to be our 16. Sigma sub x bar is going to be sigma over the square root of n. So we're going to have 1.2 divided by the square root of 100. And that turns out to be 0.12. Now let's get our z-score. Remember, for this, it looks like this. It looks like x bar minus mu of x bar divided by sigma of x bar. X bar is 15.8. Mu, a proposed mu of 16, and then divided by 0.12. Here I get to two decimal places, negative 1.67. Well, let's take a look at the area in the shaded region then. So we'll go to the standard normal distribution and get that area there. So there's the shaded region again. And now let's find out that area. This number that I've just shown you here, this is called a p-value. And here's how the p-value works. We compare the p-value versus alpha. Now we're given alpha is usually a stated significance level at the beginning of the problem. The p-value here is 0.04746. You don't need that many decimal places to see which one's bigger. You can see that alpha is bigger than the p-value. Whenever alpha is bigger than the p-value, we accept h sub a. Actually, the phrase used is we reject the null hypothesis. Then if the p-value is greater than alpha, then we reject the alternative hypothesis. So we reject the null hypothesis. If we scroll back up here, what does that mean to reject it? Statistically, we're saying we have enough information based on this sample to see that we're probably actually producing soda pop with less than 16 ounces in the can. So it is pointing to a serious manufacturing problem in the process. Now, for this last topic, these last several topics, I'm going outside of our textbook because I don't think it has enough examples for us. So I'm going to give you a bunch of examples that you can use to study from, and I'm going to do a bunch of them here. And I'll give you a whole collection of problems with solutions, or well, not solutions, but answers so that you can practice for yourself. So let's see what we have here. A researcher believes that the average number of hours a person spends in traffic each year is more than the national average of 46. So what we have here, they've already used a word, an inequality word, more than. So what you want to do, the first thing you usually want to do is set up your null and alternative hypotheses. So the more than, the national average of 46 looks like this. Mu is greater than 46. The population average is actually greater than the 46. This is what they call the claim. Then you fill out h sub 0 using the opposite symbol. So since this HA is a greater than sign, H naught should be less than or equal to 46. So let's see what we have in our sample. We are assuming the population standard deviation is 3.6, so there's our sigma. A random sample of 30 subjects, so there is our n. They list alpha for us, so we know the significance level. And the mean time in the sample was 47.8, so I'll put X bar for that. Now also, this arrow here does indicate which part of the graph is shaded. Since this was pointing to the right, this is often called a right-tailed test. So by that, I mean the picture is going to look like this. Now the proposed mean, or the mean that we're testing for, goes in the center here. We're going to put 46. And then let me put the sample mean, which is over here. That's 47.8. And this guy right here is our p-value. And we're going to test that against alpha. Once again, z-score. Reminder that it's x bar minus mu sub x bar divided by sigma sub x bar. X bar is 47.8. Mu sub x bar, that is the same as mu. Let me put this up here. We're going to put it at 46. And then sigma sub x bar is sigma divided by the square root of n. And we have, where was sigma at? They have not given, oh, there it is, 3.6. So I'll just go to 4 decimal places. Make sure you round this to 2 decimal places, 2.74. And let's draw a picture and determine our p-value using the table. Here, the p-value equals 0.00307. Well, let's do a comparison. Alpha versus the p-value. Alpha was 0.05. Our p-value is 0.00307. That means alpha is bigger than the p-value. So we have alpha is greater than the p-value. That means we reject H naught. What was that in this case? That our mean time wasted in traffic was less than or equal to 46? No, we're saying that we do believe that the evidence supplied to us suggests that we do spend, the mean actually is more than actually 46. All right, here we have another situation. So let's get, as usual, what I first try to do is get all my symbols in place. And then I'll set up the statements, the H naught and HA. The average score on SAT maths test was 515. So this will be X with a bar over it. The variable is normally distributed. Well, that's nice. Population standard deviation is 100. So that is sigma. A high school superintendent wishes to see if her students scored significantly below the national average on the test. So she randomly selected 36 student scores, that's n, as shown, at alpha equals 0.10. Is there enough evidence to support the claim? So what they're suggesting here is H not HA. What is the claim that they are making here? A school superintendent wishes to see if her students scored below the national average. So we want mu less than the 515, which was the national average. Up here, then we get greater than or equal to 515. So this here was the claim. It's also going to be a left-tailed test. And so let me draw a picture. Now we need to determine mu of x bar. I misspoke. We need to figure out the mean of the average of these scores that were given to us. So if you add them all up and then divide by, how many are these students? How many students are there? There are a total of 36 scores. So this must be 6 by 6. Plug them in, get the average of all those numbers. I got 509.0278. So we can see that is less than the 515. So she does at least have some evidence to support the claim. These test scores do average less than the national average. And now let's go ahead and get our our z-score. And denominator, I need sigma sub x. Sigma sub x bar equals sigma divided by the square root of n. Sigma was given in the problem as 100, and n was 36. So we'll have 100 over the square root of 36. And that ended up being 16.6667 to 4 decimal places. To 2 decimal places, we get negative 0.36. Draw your standard normal curve. And let's determine what this p-value is. So here we have, when we compare the p-value versus alpha, alpha was given to be 0.10, and the p-value turned out to be 0.35492. The p-value is greater than alpha. Well, what that means is we accept H naught, or what the phrasing that is actually used, and I'm not sure why myself, do not reject H naught. So the situation when the p-value is greater, we accept H naught as a conclusion. So here, what we would say in this case is her evidence, while she has some evidence to support her claim, statistically speaking, it's not significant of enough evidence to believe that the students' scores in their school were significantly below the 515. Here we're told that American adults skip breakfast an average of 50 times per year. That's what the belief is, at least. A researcher selects a random sample of 40 adults. There's our N. And finds that the mean number of times a person skipped breakfast over 1 year was equal to 51.2 times. So that's going to be our X bar. So we see that we do have some evidence that it might be greater. Assume that the population standard deviation is 3.1. At alpha equals 0.01, can it be concluded that the mean is not equal to 50? This is a little bit different than all the rest of the problems. Let me set up the H naught and HA and then go from there. Here, not equal is a little bit different. It's not less than, it's not greater than, it's not equal. Not equals always go in the h sub a section, so we simply put this. And then the opposite of that goes in the first part, and that would say that mu actually is equal to 50. So since we're testing, this is our claim, and this is actually called a two-sided test, or two-tailed test, better yet. We're going to be looking and considering that area inside of there. This is strange. I'll explain to you in a minute what's going on. But here, let's get our z value for this. Now the sigma I haven't done yet. Our sigma that was given was 3.1. And n was 40. And let's get this computation. To two decimal places, we get 2.45. Zero. Now, this is weird what you do. Since it's a two-tailed test, we're going to take this p-value here, and let's find out what it is. .00714. Now, typically, you're going to compare the p-value versus alpha, right? And the way you typically do it is you might split this up into two pieces and take half of the area and put it at the other end. But I think I have a way that's a bit nicer to do it. Instead, what we're going to do is we're going to consider half of alpha and compare it with our p-value. So take a look at the p-value was 0.00714, and then 1/2 of alpha is, remember, alpha was 0.01, so half of that is 0.005. Here, the p-value is greater than that half alpha, so that means, as before, we accept or do not reject H naught. Let me give sort of an indication why. Here's what happens in a two-tailed test. This is not important for what we're doing, but if you want a little bit of understanding why the thought process is the way it is, I'll explain to you. When you're given an alpha level, if it's two-tailed, we divide alpha evenly between the left and the right side. So this would have been 0.005, and over here also would have been 0.005. So alpha is broken up into two pieces like that. Then when we found our p-value, our area was bigger than half of the alpha. So this guy right here is outside of what they call the critical region. This little shaded region here is called the critical region. Well, when the p-value is bigger than alpha, that means the actual cutoff score is bigger than the critical region. That's the idea behind the geometry behind it. So we can see, but we just need this. When there's a two-tailed test, we need to consider only half of alpha and consider our p-value versus half of alpha. So we have our cases now. In general, if p-value is greater than alpha, we do not reject H naught. On the other hand, if the p-value is less than alpha, we reject H naught. And sometimes you're going to have to test for half alpha. So p-value versus 1/2 of alpha. If it's less than 1/2 alpha, reject H naught. And finally, the p-value is greater than 1/2 alpha. We do not reject H naught. Of course, these are only for the two-tailed test. It is the most painful of the tests, I agree, but it has to be dealt with because less than or equal to, less than or greater than are not enough to take care of every possibility. We also must look at not equal to. A researcher wishes to test the claim that the average cost of tuition and fees at a four-year public college is greater than $5,700. So they've already given up the game already. Here I already know how to set up my H sub 0 and my H sub A. Greater than 5,700, so we know mu is greater than 5,700 is the claim. Notice that's a right-tailed test. So H naught must be the opposite of that claim, less than or equal to 5,700. Now let's go ahead and get our the numbers. 36 here is n. The mean, this is the mean of the sample, so this guy right here is equal to x bar. The population standard deviation is 659, there is sigma. And then we're going to use alpha equals 0.05. In fact, this book states that if no alpha is given, you might as well just assume that it's 0.05 because it's such a standard use. Well, let's draw a picture. Here's our 5,700, 59, 50. And there's our p-value area. Well, I usually don't remember to do this earlier, so I'll do it right now. This is sigma divided by the square root of n. Sigma is 659 divided by the square root of 36. So I'll take it to 4 decimal places. And now we're ready for our z value. I'll write down the formula again just to remind you. We take x bar minus mu sub x bar divided by sigma sub x bar. To 2 decimal places, I get 2.28. Let's check that p-value. All right, now it's time to make our decision. So let's compare the p-value with alpha. My p-value is 0.01130, and my alpha is 0.05. Well, alpha is greater. That means we reject H naught. A researcher claims that the wind speed in a certain city is 8 miles per hour. They use is, that is an equation. So I'm going to put H naught, mu equals 8. HA, mu does not equal 8. So this was the claim in the first spot. This is a two-tailed test. To me, these are the most annoying of the tests, but at least you got a way to look at it now. Remember, you're going to have to cut the alpha in half. So when you're looking at this here, what you're really going to compare the p-value to is alpha divided by 2. That's 0.025. Now let's get our information here. We had an average wind speed of 8.2 in the sample, so that's X with a bar. There's our N. There's our population. There's sigma. Now let's draw a picture. We put 8. Now our p-value will simply be this area inside of here. Since it's on the right, we have to shade to the right of the p-value, or the mean that we measured. Let's go get a sigma sub x bar while we're here. That's sigma over the square root of n. That's going to be 0.6 divided by the square root of 32. 0.1061. Let me get the z value here. So my x bar then 8.2 minus, where's my 8? Divided by 0.1061. We get 1.89. 1.89. Check out that p-value. P-value that I got was equal to 0.02938. And so now let's compare the p-value with 1/2 of alpha. Since this is greater, do not reject H naught.